Hey folks, Dr. G here with today's lesson on rotational spectroscopy. So we're going to be just dipping our toe into the waters of rotational spectroscopy today. Basically, our overall goal is we want to be able to fully explain the Rovibrational spectrum of HCl. And in order to do that, of course, we're going to build that up from a foundation of quantum mechanics, starting from the rigid rotor. So if you've not yet watched my video on the quantum mechanics of the rigid rotor, definitely watch that first. So all that being said, I hope you enjoy the video. Alrighty folks, let's get into it. So as mentioned, we are just going to be beginning our discussion on the quantum mechanics of rotational spectroscopy today. So there's a lot to cover, but believe it or not, there's even more than we're going to do today that could be covered on this topic. So without further ado, let's get started. So first of all, why spectroscopy, right? Why is this such an important thing in chemistry? Well, as chemists, we want to know what the molecules are doing, right? At least what are they doing if we look at them, right? And so basically, molecules interact with light of different wavelengths for different reasons. And this is sort of a core principle of spectroscopy, is that, if we want to probe what the molecules are doing, we have to use the right wavelength of light to try and spy on these different actions that they are doing when we look at them. So of course, another fundamental principle, conservation of energy. It's never created or destroyed, only converted or transferred. And this is going to be really important for spectroscopy to keep this in mind during the entire discussion. Thus, if a quantity of energy completely leaves one molecule, well then it must have either transferred to another molecule or it's been converted to light. And if that energy exits as light, well then that light is going to have a characteristic wavelength that's corresponding to the change in energy that the molecule experienced when it transitioned from a higher energy state to a lower energy state. So, if we study the way matter interacts with light, and then make these measurements and then combine that with some theory, then we can put together a reasonable explanation of what the molecules are doing, right? What their actions are that correspond to these measurements of the light. And that's really crucial to spectroscopy. So now I'd like you to take a moment and think about the different changes in a molecule, right? Actions a molecule can do, where it goes from a higher energy state to a lower energy state. And your hint here is think about the types of motion that were demonstrated with our quantum mechanical toys, right? Our toy problems, such as, say, the harmonic oscillator, the rigid rotor, things like this. So here's three examples that I can think of off the top of my head, right? We have rotational states, right? We go from a higher angular momentum to a lower angular momentum. Or transitions from vibrational states, right? If you have a molecule, maybe there's a single carbon-carbon bond that's vibrating in a certain way, and it goes from a larger energy vibration to a smaller energy vibration, right? That would actually also correspond to energy being released as light. Or we could talk about spin states, right? In particularly, I'm thinking of NMR spectroscopy here, right? If you have a high spin state relaxing to a lower spin state, that's going to give off light as well. And of course, when I say light, I'm referring to electromagnetic radiation of all wavelengths, right? Whether or not it's visible. So I just talked about, light exiting the system that we're studying, right? Where the system went from a higher energy state to a lower one, and we measure the light coming out of it. Well, what about the other direction? Can you maybe think of a way that we can study our system going from a lower energy state to a higher one instead? Yeah, of course. UV-vis absorbance spectroscopy, right? This is a really common way of doing this, where essentially you send light through your sample and you control which wavelengths are going through at a given time so that you can see which wavelengths are being absorbed and which ones are not. And from that, then we can deduce information about the molecule by which wavelengths are being absorbed, which we can tell by quantifying how much light is making it to the detector. And of course, as mentioned in the title, we really want to keep quantum mechanics front and center in our discussion of spectroscopy. So let's review some of these core principles here. So here we have the Hamiltonian acting on our time-independent wave function, little psi, and then that is going to, little psi is going to come out unscathed, but it will be multiplied by the eigenenergy. And so this is our time-independent Kronecker equation, which we've seen many times throughout the series. And then, of course, we can split that Hamiltonian into the kinetic energy and the potential energy operators. And again, if energy is quantized, then both types of energy here, both kinetic and potential, must also be quantized. So basically you get quantization due to motion, which is reflected in our kinetic energy term, and also quantization due to position, right, which is determined by our potential energy term, right? If you stretch out a spring, right, that's potential energy due to position, right? Where are the two masses relative to each other? How stretched out is it? How stretched out is a chemical bond, perhaps? So here we are reminding ourselves of the translational energy of a particle that is confined to some space. And, as we've mentioned before in this series, the potential energy function certainly matters here, right? Because that's what's keeping the particle confined. But given that it is confined, its energy is determined by its translational energy, its kinetic energy inside of this neutral space. So our conversation on the particle in a box was focused on the kinetic energy, specifically translational motion, kinetic energy of a particle that is confined to some container that is infinitely strong. And of course, we also looked at the quantum harmonic oscillator, which is going to be very important for today's discussion. So in this case, both the potential and kinetic energy terms are always important because there's going to be some contribution depending on where the oscillator is in its motion. It can stretch, it can be compressed, it can vibrate essentially, right? So our quantum harmonic oscillator is a really great model for trying to understand how molecules vibrate. And of course, if you have any experience with Fourier transform infrared spectroscopy, right, FTIR, that type of methodology is typically all about studying these vibrational motions, right? Maybe you look for a carbonyl stretch where a carbonyl bond has some characteristic way that it vibrates, and that interacts with light in that infrared region. And of course, our rigid rotor quantum toy problem here, right? That's of course going to be important for rotational spectroscopy because we're going to be talking about molecules rotating. Here we have another slide from the quantum rigid rotor video. So if you have not seen that one yet, I definitely encourage you to watch that first before this video, as that particular video really focuses on the fundamental concepts to help you understand how energy is quantized in a context where the energy we're talking about is kinetic energy, and more specifically, it's kinetic energy due to angular momentum. I encourage you to maybe pause the video for a moment and focus on that equation at the top, right? That energy equals Bj times J plus 1 plus A minus J times K squared, right? Because that was the one that dealt with the energy levels due to rotation, but specifically for the symmetric rotor. And remember, there's different types of rotors. The symmetric rotor was one type. And of course, on this page where we show some equations, the top one has to do with the linear rotor, and the bottom one has to do with the symmetric rotor. And that linear rotor equation at the very top, we're going to go over that one quite a bit because HCl, right? HCl gas, hydrogen chloride gas, is one of these sort of classic examples of looking at rotational spectroscopy, and we're going to look at it, and that certainly qualifies as a linear rotor. Now, one of the concepts we're going to spend quite a bit of time deriving in this lesson are something called selection rules. And basically, in the field of spectroscopy, there's going to be certain transitions in energetic state that are allowed and certain ones that are forbidden. So allowed transitions and forbidden transitions. Now, do I mean the scientific community won't allow you to do these things? No, nature won't allow you to make some measurements, right? Some measurements cannot be observed because, in the end, right, this is quantum mechanics. The observation process is fundamentally a part of it. You can't pull that out of it and say, well, what was it doing if we didn't look? Well, that's a poorly formed question. Or maybe it's not fair to say it's a poorly formed question. It's just the sort of question that we don't know how to answer, right? Because the observation is fundamentally a part of quantum mechanics. So there are certain things we can observe, certain energetic transitions from maybe one rotational state to another. Some we can observe and they're allowed, and some are forbidden by nature. And those are, we say that they're forbidden. And so this idea that some of these things can be seen, some cannot, we call these selection rules. So basically, like if you're going to make an observation, it can only be selected from certain allowed transitions. So we call this selection rules. Now, one of the simplest, if we're talking about rotational spectroscopy and, a neutral field, right, we're not going to distort the molecule in any way. With a field, we're just going to observe it as it is. There's the one simplest rule is called the gross selection rule. And there's a very nice definition of that in the physical chemistry textbook cited at the bottom by Atkins and Dipoles. So I'm just going to quote it directly. The gross selection rule for the observation of a pure rotational transition in the microwave spectrum is that a molecule must have a permanent electric dipole moment. That is, to absorb or emit microwave radiation and undergo a pure rotational transition, the molecule must be polar, right? So like something like methane, right? Think about methane and electronegativity. That's really balanced, right? You wouldn't want to try and look at methane using this technique, but something like water, right? That definitely has a dipole. And notice that purely rotational spectroscopy is microwave spectroscopy. But as we get through the discussion here, we're going to look at FTIR, right? And we'll see why the two go together later. But, I think it is important that they stress this in the book that, for a pure rotational spectrum, that's microwave spectroscopy. And also from that same textbook is that nice image at the top right. That figure shows that a rotating polar molecule is going to look like an oscillating dipole. And an oscillating dipole, well, that can stir the electromagnetic field into oscillation. And so maybe that's a lot, looking at a picture to see that. So I've put together sort of a little animation. It's nothing too fancy, but I think it'll kind of bring that point home even further. So this isn't the one I'm talking about, right? So, but this is also an animation, right? So here's a GIF that I got from Wikipedia, where we see light. Right, so light has an E field and a B field, right? The electric field and the magnetic field is the B field. And we see that, they travel in this way. And you can imagine that, okay, if the light is traveling like that, but you're not moving relative to the light, right? Because if you think about how fast light moves and how fast a molecule moves, it's no contest, right? Basically, that molecule is stationary compared to how fast the light is traveling through it. So if this relatively stationary molecule with a dipole is just sitting there, like we see at the bottom right there, then that dipole is going to experience an electric field going back and forth. So at one point, the dipole will try and align with it one direction, and then it's going to try and align the exact opposite direction, right? Because the electric field, as we see, is oscillating. And so there's a really nice tool from PhET, right? The simulation folks at University of Colorado Boulder put that together, right? The PhET simulations. They're great. Check them out. I put this figure together using that. And basically, if we have this dipole hanging out in this field, right? So I put a bunch of positive charges at the bottom to show an E field. And so stare at this molecule for a second in this field and think, all right, what would I expect that molecule to do? If there's all that positive charge at the bottom and the molecule has a dipole, right? It's negative on the left and it's positive on the right. Well, we would expect to see it rotate, right? We would expect to see the molecule move like that. So basically an E field applies a twisting force called torque to a dipole. So if a molecule has a dipole and it's in an E field, it's going to experience a twisting force that we call torque, right? So with cars, a lot of people, one thing they want to know, how many foot-pounds of torque does the car make, right? If it makes 350 foot-pounds of torque, like that's going to be a pretty quick car, right? Because that twisting force rotates the wheel, and the part of the wheel through the tire that contacts the ground pushes backwards, but then friction pushes the other way and it propels the car forward. All right, so that was a stationary E field, right? If we just have a bunch of positive electric charge, we showed that it applies that twisting force. But again, we said light oscillates, right? That E field is going to go back and forth. So what about an alternating E field? Well, so I put together a few more figures like this. And so let's say the positive switches to negative, right? So the molecule is in this position now. It had just gotten pulled down, and now the local field switches to negative. So now that negative side of the dipole is going to get repelled, and the positive side is going to get attracted. And then now it switches back to positive. Okay, well now the negative side is going to get repelled, or excuse me, the negative side is going to be attracted, and the positive side is going to get repelled, like that. Then it switches, and then again, it gets repelled from the negative side, and the positive side gets attracted, right? So that twisting force is going back and forth. That's alternating. And essentially, this is how microwave ovens work, right? Microwave ovens heat your food like this. The frequency of the microwave light is tuned to basically the dipole of the water and how quickly the water is able to rotate back and forth, right? You tune that microwave frequency light to that so that the dipole on the water molecules gets twisted back and forth like this. And that back and forth motion of twisting the water around, well, then that makes the water molecules knock into each other, and basically we get thermal motions, right? The molecules in your food in the microwave are getting jiggled around all over the place because we keep twisting the water molecules vigorously back and forth, and that's how your food gets hot. All right, so you've seen how, in a situation like a microwave oven, that you can apply electromagnetic radiation in the microwave region of the spectrum, and you can make the molecules twist back and forth. But what if a molecule just happens to be freely rotating? If a molecule has a dipole and it's freely rotating, well, then wouldn't that also produce an oscillating field? So that's what we're going to look at with these next few simple animations. So again, using that FET simulator, you can set things up so that they have this little equipotential meter here, right? And it'll tell you how many volts it's measuring. So I put that right there. I parked it at the bottom there. I'm not going to move that. But what I am going to do is I'm going to rotate that dipole there. So this is going to be our first measurement. And we see that it reads at a little over -6, right? So that's our first point. If you look at the top left, that blue point there is at about -6 volts. And let's rotate it. Let's rotate this dipole about 90 degrees. And if we do that, so now we've rotated the molecule about 90 degrees, right, or pi over 2. And we see now that the equipotential meter is reading a much smaller voltage, right? Now it's reading pretty close to 0, right? It's minus 0.063. So now it's a very small value. Now let's rotate it another 90 degrees. So now it's all the way up to pi radians. And now we see that the equipotential meter is reading positive 6.2 about. So we plot that at the top left, rotate it again. All right, now it's very small again. So, we're just rotating 90 degrees at a time like this. And of course, if we wanted to get more fancy with this, right, we could do a lot more angles in between the ones we're looking at, right? But in the interest of time, I think, this is good enough for now. It's a little crude, right? That would not actually be pointy like this, right? It would be smooth. It would look like, it would look like a trigonometric function, right? Like a sine or a cosine. And of course, it's easy enough to imagine if we keep doing this, we're going to get this oscillating pattern. So basically, we're measuring an oscillating voltage. So if you have a freely rotating molecule that has a permanent dipole like that, and you happen to have an instrument that's measuring this voltage like this, then yeah, you better believe it, you're going to see an oscillating electric field due to a rotating dipole. So again, just as an electric field can apply a torque to a dipole, so too can a rotating dipole generate an oscillating electric field. All right, so moving forward with our discussion of the quantum mechanical explanation for selection rules, we got to get back into doing integrals with our wave functions, right? So remember with our good old one-dimensional particle in a box, right? We have these different energy levels that was determined by the quantum number n. And so that subscript n or m, they're both for n, but basically it's so that, we can call one a different value than the other, right? That's why we're using two different indices here for n and m. But remember, let's say we have the wave function for the ground state, right? So n equals 1, and then we have the n equals 2, right? Let's go first excited state to n equals 2. Because remember, the particle in the box, the lowest value for n is 1. And so if we did that, and we plug those two wave functions in, well, we get what we call a Kronecker delta type relationship here, right? Where basically if n equals m, then this integral is going to give you 1. But if n is not equal to m, that integral is 0, right? And we said that this is orthogonality. It's an orthonormal basis set, right? We've talked about all these things before, but I just wanted to remind you of it. And again, if you haven't heard of any of this stuff, definitely watch the earlier videos in this YouTube playlist where I go over these concepts. And another concept we need to remind ourselves about is expectation value for an observable, right? So that same integral I just showed you, right? This one, you basically make a sandwich, right? You make a wave function sandwich. If you put the observable operator in between psi star and psi, then this will tell you the expectation value for that observable, for whatever you want to observe, right? So if we, let's say we want to observe the position for the quantum harmonic oscillator, right? If we put that in there, we plug in x, and then we carry this out, well, then we're going to find out that the expectation value for x is actually 0. And if you look at the symmetry of that harmonic oscillator, this is not surprising, right? No matter how high the energy level goes, given the symmetry of the potential energy function here, right? This harmonic oscillator potential energy function, not surprisingly, no matter how high the energy level goes, the expectation value for the position is always going to be 0, right? Because that's where the equilibrium point for the oscillator is, right? If you think of it as a spring, neither compressed nor stretched, right? That's the position that, right, if you measure the position a whole bunch of times and you take the average, that's what you expect to see. So that's not at all surprising, but I wanted to remind you of this relationship as well. So that was the expectation value of position x. So again, simple interpretation, the average position of the quantum harmonic oscillator is at its equilibrium point. But this doesn't tell you the whole story. You know, like with anything statistical, the mean often doesn't tell the entire story, right? We want some other metrics, like maybe standard deviation or the variance or the mode or the median, right? There's other ways of looking at statistics other than the mean. And here's an example right here, right? If we look at the expectation value of x squared instead. And so importantly, right, when we calculated the expectation value of x squared, we found that that is not equal to 0. And in fact, that one does change depending on the energy level where you are vibrating, right, where your harmonic oscillator is vibrating. If it's vibrating more wildly, right, higher energy, that's going to get broader, right? That's basically, if you look at the distribution of where you're going to observe the oscillator, right? That mean it's going to, the center of that distribution is going to stay at 0, but it's going to get fatter and fatter the higher in energy you go. And you can actually quantify this by taking the expectation value of x squared. So I just wanted to remind you of this to show you of an integral where you take the expectation value of an observable and you do not get 0. So building on this notion, in order to observe an event where a system transitions from one energy level to another, for example, from quantum number n equals 1 up to quantum number n equals 2, right? Transitions from the energetic state corresponding to n equals 1 or quantum number n equals 2, right? This is a sort of transition that we can look at. Well, then this integral below needs to have a non-zero value. So basically, we still have a wave function sandwich here, right? We've got our operator in the middle there, A, that thing that we want to measure. And on the right, we have the initial state psi 1. And then we have psi star of our wave function for quantum number n on the left, right? So we have psi star of that. That's the complex conjugate. And so this is the integral you need to take to do selection rules. Basically, some of the time, you're going to get a 0 integral here, and then that's a forbidden transition, right? Like, let's say this integral gave us 0. Well, then we would say the molecule is, you know, we're unable to observe a transition from state n equals 1 to state n equals 2. We say that's forbidden. And I put this little note in here because I want to make absolutely sure that everyone notices, right, that we have psi 1 and psi 2, and we have the operator here, right? Because if you took away the operator, it just becomes that Kronecker delta relationship, right, where you know it's going to be 0 if those subscripts don't match. Well, that's not the case here. When you put the operator in there, it is possible to see integrals that are non-zero going from different wave functions. So I just want to make sure that this is crystal clear to everyone that, you know, this is not a Kronecker delta kind of situation, right? And that's because that operator is in there for an observable. One other thing that I wanted to talk about is a notation thing, right? We call this Bra-ket notation. And this is a nice, really compact way to write these integrals, right? Because again and again, we're going to be doing these integrals where, you know, you have psi star psi or psi star times an operator times psi, right? And we're integrating over all space, right? We have to do this so often. You see that that's kind of bulky to write all of that out. And so basically, we have this Bra-ket notation where, you know, why do we call that, right? Bra-ket, bra and ket. This is the bracket. So basically, that's what we have here. So psi star is the one with where the, you know, the bracket's kind of pointing to the left, and then psi is the one with the brackets pointing to the right. And we can put them together to do these integrals over all space. And then, of course, if we want to put an observable in there, right, the observable operator, you just throw that in the middle of your Bra-ket like that. Right. So as I said, we're focused on this transition dipole moment, which is basically how we're going to determine which transitions are forbidden or allowed. And before we do that, though, what's a dipole moment? Let's look at the quantum dipole moment operator before we move forward into the transition dipole moment. This is our linear rotor, right? Where we have two atoms, maybe like a hydrogen and a chlorine, right? Bonded together. That would be an example. And we see that the magnitude of the electric dipole moment can be calculated as Q times R. So whatever the value of Q, that charge is, and then the distance between the charges. So this is for, this simple system. But let's also show the general definition here, where it is the sum of every charge multiplied by the vector representing that charge's position. So all of those R's, right? R1, R2, etc., those are position vectors, right? And maybe X, Y, Z or R theta phi, right? These are the position vectors, and that is multiplied by the charge Q. So you can have different charges, as many as you want, and as many positions as you want, and this is what you have. And then so if you were going to do the transition dipole moment calculation down there, that's what we see in that integral, where we have psi star B. And sandwiched in there, we have all of those charges multiplied by their position operators, and then psi A, right? So we're going from state A to B, and of course we have our dipole moment operator sandwiched in between those two wave functions. So of course we have a nice compact way to write sums, so we might as well use it. We have the dipole moment operator is that mu hat. And that's going to be the sum of all the charges multiplied by their position vectors R. And then now that we have this nice compact Bra-ket notation, then the transition dipole moment is just going to be that simple expression at the very bottom right. So now, thanks to our nice Bra-ket notation and having defined the dipole moment operator, if we look at that, we have the expression that we need to determine if it's going to evaluate to 0 or not, right? For our selection rules, right? Because we want to get selection rules. And so looking at that thing, what is the simplest way you can think of that this dipole moment operator sandwiched between psi B and psi A, right? What's the simplest way you can think of that would be equal to 0? Well, if the dipole is 0, right? If mu hat is 0, well then, yeah, that's going to be 0. Okay, so then mu hat equals 0, what does that mean for a molecule? Well, it means that it doesn't have a dipole, right? It doesn't have a permanent dipole. And if you remember, back when I showed you that definition for the gross selection rule, that's what it was, right? It says that, okay, if a molecule doesn't have a permanent dipole, well, then observing these transitions between rotational states is impossible, right? There's no way to make that measurement. And if you're wondering, well, how can that be possible, right? That there's absolutely no partial charge on any of the atoms in the molecule? Well, no, it's not that so much as they all balance out, right? Like if, again, thinking about methane, sure, there's some difference in electronegativity between the carbon and the hydrogen, right? It's small, but it's there. But nonetheless, it's balanced out with methane. Right, those hydrogen atoms. Remember, we talked about spherical symmetry. So go back to that previous lecture if you forgot about spherical symmetry. But basically, yeah, that's going to be all perfectly balanced out. So if you add up all these vectors, they're just going to balance out, and you are going to see that the dipole moment operator is going to add up to 0. Okay, so we've derived the gross selection rule. So to put it all together, we can say that the gross selection rule means that observing transitions between rotational states using spectroscopy is forbidden, right? Meaning it's impossible, you can't do it, for molecules that do not possess a permanent dipole. So to give you two well-known examples, water does have a permanent dipole, methane does not. But is that the only way that this integral can evaluate to 0? Well, no, probably not since I'm asking you, right? So no, that's not the only way. So we went over the gross selection rule, but there are other selection rules. So I'll explain, but in order to go over that, we need to go over some mathematical background first. There is a notion in mathematics of even functions and odd functions. So here's the definition here, right? If f of minus x is equal to f of x, then that's an even function. But odd functions, f of negative x is equal to negative f of x. And this is, this is pretty clear, but it's even clearer if you see an image. So if you look at that cosine function, if you say f of x and f of negative x, you're going to be on opposite sides of that symmetric function, right? So if I take f of negative pi and f of pi, it gives me the same height, right? So that's an even function. On the other hand, looking at the sine function, if I take f of negative pi over 2 versus f of pi over 2, it's going to return the same magnitude, right? But the sign's going to be opposite, right? So on the left side, we're at -1. On the right side, we're at +1. So if you want to make them equivalent, you just have to say that f of negative x equals negative f of x. But of course, it goes further than this, right? So there are more things that we can know about these even and odd functions, namely their integrals. So here I have some examples that I put together for you using the software Mathematica. And we have some even functions in blue and some odd functions in red. So I have red boxes and red lettering for the odd functions and blue for the even ones. And I basically cooked up some functions by multiplying exponentials by trigonometric functions, right? Sine versus cosine, and put in different values for frequency. So that's how I created these, right? These are just some examples of even and odd functions. And the reason I did it in this way is because if you integrate them over all space, notice that the even functions are giving you some constant value, right? Like at the top left, we have that square root of 5 pi over 2 all divided by e to the 5 over 2, right? That's what we have at the top left. But then if you look at the odd function, that's 0. So they both came out to 0 for the odd functions, and the even functions gave you some constant value when you integrate them over all space. And of course, with our wave functions, right, we're multiplying those together and integrating over all space all the time, right? We've been doing a ton of that in this course. And speaking of multiplying functions together before integrating them, an interesting relationship here is that if you multiply an odd function by an even function, that gives you an odd. If you multiply even by even, that gives you even. And if you multiply odd by odd, that gives you even. And of course, I didn't want to just tell you this rule and have you just believe me. I wanted to show you examples. So if you look in the center here, I'm multiplying the odd function 1 that I created and the even function 2 together. So that's odd times even. And that's an odd function. And if it's integrated over all space, we do get 0. And just sort of eyeballing this, right? So let's convince ourselves that this is true. Do you notice how for that odd function, do you notice how the amount of area that's above the x-axis perfectly balances with the amount of area below the x-axis, right? You can eyeball that and see it, that basically for every time there's an upward pointing lobe, there's a downward pointing lobe of like the same, size and shape. That symmetry is very easy to see by eye here. And of course, even times even, if you look at that, it's clear that that central lobe is a lot bigger than the up and down ones, right? For that even times even. So it's not surprising to look at that, yeah, that's going to give you some finite positive value. And then of course at the bottom, similar thing, right? We have some downward pointing lobes and we have some upward pointing lobes, but we see that the two upward pointing lobes, even just by eye, it's pretty clear to tell that there's more area above the curve than below it. So I encourage you to pause the video here and, stare at all of these functions and sort of convince yourself visually that these zero and non-zero integrals, they make sense to you. So we've shown that it's possible to know that a particular integral over all space will be 0 if the function being integrated is odd. And we've also shown this relationship that multiplying even and odd functions together has a predictable pattern, right? Odd times even is odd, even times even is even, odd times odd is even, right? This is the pattern. Now, what's so great about this for quantum mechanics is if all we want to know is whether or not a particular transition is allowed, we just need to know whether or not the integral is going to come out to 0 or some non-zero value. Essentially, we don't actually have to take all of those integrals, right? We just need to figure out, is the integrand, right? If everything being multiplied inside of the integral, does that give you an even or odd function? Then we can know this. So it's crucial that we can show that all of the functions inside of the integral are either even or odd, right? If we can look at that big function of all of them multiplied together and kind of separate it into be like, okay, this part here, that's an even function. This part here is another even function. This one's an odd function. Well, then you would know that, even times even is even, and then that even times odd, that's odd. So overall, that's going to be odd. All right, so that is even and odd functions. Now notice this is just in one dimension, so let's start thinking about what do I mean by even and odd functions in this three-dimensional space, right? In our spherical coordinates that we need to work in for our molecules here. And the main purpose of this slide here is that I want to show you what these symmetry operations look like, right? So for the even and odd functions in one dimension, we just sort of looked across, what's on the other side of the y-axis, right? But here it's a little different. You actually have to basically imagine turning the structure inside out. And so I really like these animations that I found from that YouTube video cited below. And we can see that for these two molecules, basically you choose a center of inversion, an inversion center, and basically you imagine every point going through that center. So looking at that ethane molecule on the right, if you imagine that hydrogen that's pointing up on the right, that one goes through the inversion center to the other side, and then it would end up as the hydrogen atom that's pointing down. So I really like this molecule example as a place to sort of bring up this topic of inversion through a center. Also, I use the word parity here because I wanted to make sure that you're familiar with this term, that basically it's said that the object has parity if the symmetry operation produces something that looks just like what you started with, right? It has symmetry with respect to that operation. So that's known as parity. All right, so now that we have introduced this concept of parity using a molecule, which is basically like the even and odd situation in 1D, let's look at a wave function in 3D. And before we do that, basically, we need to consider that these wave functions have a phase to them. So that's what's going on with the coloring of those lobes, right? They have a color to them. That's the phase. So what's the phase? Well, okay, let's think back to our one-dimensional particle in a box. And remember how when we looked at the probability density functions, right? You multiply psi star by psi, that gives you a probability density function. Everything's positive, right? There's no negative probabilities. But the wave functions themselves, right? When we watch them oscillate, right, they were kind of fun to watch. They would be both positive and negative, and that was the phase to them, right? They also had a phase to them, and that's easy to plot in for a one-dimensional function, right? Because there's only one spatial dimension, so then we can use that other dimension to show the phase. Well, we can't do that now, right? Because this is a wave function that exists in a three-dimensional space. But what we can do now is we can use colors. And so that's what we do to show the phase here. And again, just like the wave functions for the one-dimensional particle in a box, that remember we had a real and we had an imaginary component. Together they're the whole wave function, right? But there's a real part and there's an imaginary part. And so that's what we're showing here, that basically the phase of the real part versus the imaginary part in both cases here. And what are these wave functions for? Well, if you think all the way back to the hydrogen atom, right? We talked about the hydrogen atom, and remember we used the principle of separability to separate the radial component of the wave function from the angular component of the wave function, and we gave it the name y, right? So this is the angular component of the wave function here, and we also call these things spherical harmonics. You might remember that's part of this here. All right, so how do we then examine the parity of these wave functions? Well, if you imagine that process where it was kind of like turning it inside out, that's basically what we do here. And if you go from one side to the other, does it change color or does it stay the same? Well, if we look at this one all the way left here, right? So if we look at this one here, if I start at this red lobe here and I invert it through the center, now I'm down here on that red lobe. I'm at the same position, right? It has symmetry. These lobes are the same either side, right? It's in the same, it's basically, if I'm in the top part here, then I'm in the bottom part here, and the color's the same, right? The phase does not change going from up here to down here. Same thing with that cyan colored one, right? If I go from up here, then I'm gonna come out down here, right? So the top one is even, it has parity. The bottom one, nope, that one's odd. If I go from up here to down there, okay, fine, the position's the same, but the phase definitely flipped. So this is odd, this is even. The top one is even, the bottom one is odd. And then again, comparing that to the images on the right, essentially we just check the phase after inversion through the origin for the 3D example versus checking the sign after reflection across the y-axis in the one-dimensional example. So we can see that these things are definitely analogous. And, we have an intuitive way of thinking about it, but it's also good to see the formal version as well. That's sort of this process that I said, okay, we start at the top over here, we come out on the bottom after inverting through the center. This is what it is formally, right? That R is R, and theta goes from theta to pi minus theta, and phi goes from phi to phi plus pi. So this is basically how it goes. And again, we see that like sign change there. And what's really nice about this concise way of writing it is that we can see that we have parity for even numbers of L, right? You won't get a sign change. And parity is violated if L is an odd number. So the quantum number L here will determine parity for us. Okay, so as promised, the whole reason why we went down this path is that we were trying to understand how else you could get zeros for this integral here. And basically, to put it concisely, there is a way for this integral to be zero other than when, of course, mu hat is zero. And it'll happen when the product psi b times the mu operator times psi a results in an odd function, because integrating odd functions over all space results in a zero integral. Okay, so we know we have to check for an odd function, but how do we do this, right? Well, okay, so psi b and psi a, for our particular use case of a linear rotor, those things are going to be spherical harmonics. We actually already know if those are even or odd. So the first thing we're going to want to do here is let's check and see if mu hat is an even or odd function. Can we demonstrate this? Again, we begin with our definition of the mu operator, right? That sum of all the charges times their position vector r. And because we're going to be focusing on a linear rotor, we can actually simplify this to q times r, because we only need one charge and one position vector. You might say, well, wait a minute, there's, if it's like HCl or something like that, right? Isn't that two charges? Well, we choose the coordinate system, so let's put 0, 0, 0 where the nucleus is. And in that case, then that zero vector is going to get multiplied by the nucleus's charge. And moving forward from that definition of mu hat, let's consider the simplest example, a single electron atom. Right, because we are going to be invoking the angular wave functions, right? And that's where we got them from in the first place. So we're going to start there. So therefore, we can define mu hat quite simply, right? We could just say QR. And you could say, well, hang on, the proton and the electron, and let's say a hydrogen atom, for example. Well, we could put the coordinate system however we want. So let's define the point 0, 0, 0 as being the location of the nucleus, right? So that's why we really only actually have to worry about the charge on the electron and the position of the electron. So not surprisingly, mu x is minus the charge of an electron times x, mu y minus ey, mu z minus ez, right? Where e is just the quantity of charge on an electron. And of course, you probably noticed I said x, y, z components for the moment, right? Because, we need to be in spherical coordinates again. So if we look at, let's just look at z, for example, right? Of course, there's three that we can look at. Let's choose z. Turns out we can get z is equal to r cosine theta. That's the transformation to go from z to in terms of r and theta. So mu z we're going to define as minus er cosine theta. And if we recall, or maybe look up a table of spherical harmonics, is probably more likely, we'll see that the spherical harmonic for y10, right? So L is 1, M is 0. If we look that up, that's the square root of 3 over 4 pi times cosine theta. So we can go ahead and express that in terms of y10, of the angular wave function y. And what did I just tell you earlier about the angular wave functions is we actually do know the pattern that they follow for even and odd. So if we can express this in terms of even and odd functions, then that can give us a really nice clean way of knowing whether an integral is going to be even or odd after all of its components are multiplied together inside of the integral. And so now we have mu z expressed in terms of the spherical harmonics. But why? Why is this beneficial? Why did I do this? Well, spherical harmonics, we know that they're going to follow some sort of even and odd pattern, right? I hinted at that early on in this section. And here we see a few examples of this, right? So if we have a y10, if I integrate that over all space, it's 0, and that's odd. And then y20, integrate that over all space, it's even, and it gives us square root of 5 pi over 4, right? i.e. not 0, right? That's the important thing here. And then, of course, odd goes back to 0. So this follows a consistent pattern. So we know that y10, that's an odd function. And you say, okay, well, it's multiplied by some stuff. But if you look at the stuff that it's multiplied by, 4 pi over 3, square root of that is a constant. The charge of an electron is a constant. And R, of course, if we're talking about a rigid linear rotor, R is fixed. That doesn't change. Or really any rigid rotor, right? Those positions are fixed relative to each other. And you might say, well, hang on a second, Dr. G. We were talking about hydrogen there, and I went from a little r to a big R. Are we allowed to do this? And yeah, if I had left that as a little r, well, then these integrals we're taking, that little r would have come outside the integral anyway, because the integral's not with respect to that, so it's treated as a constant, comes outside anyway. And just to note, we've only addressed the z component of mu here, but, we could keep going and do the other two as well. But in the interest of time, we'll leave it at that. But yeah, the same process carried out for mu of x and mu of y would fully demonstrate that mu hat can be expressed in terms of y sub 10. All right, so now that we've shown that not only the wave functions for our rotating molecule with a permanent dipole can be written in terms of spherical harmonics, but also the dipole moment operator itself can be written in terms of the spherical harmonic for L equals 0, which here we've switched it to J, right? Because now we're talking about rigid rotors, but again, these same spherical harmonics, they show up in both cases. And basically all three of the functions inside the integral are spherical harmonics, and we know which spherical harmonics are going to be even or odd. So now finally, we know whether our integral is going to be 0 or non-zero, right? If it's 0, it's a forbidden transition. If it's non-zero, it's an allowed transition. So now we have an expression that we actually don't even have to take the integral to know whether or not it's forbidden. And also, just to make sure the notation is clear, that d tau, that means we're integrating over all angles, both theta and phi, all possible values of those two angles. So now, this partially explains the selection rule for the allowed rotational transitions in linear rotors. And here's the selection rule at the bottom, right? Delta J can only be +1 or -1, right? So delta J can either go up by 1 or down by 1. That's it. And also delta M sub J, right? That's our M quantum number. That can either not change at all, or it can go up by 1 or down by 1. These are the allowed rotational transitions, and you're probably thinking, you're kidding me, we still haven't demonstrated it fully. Oh, there's a little bit more to it. We're almost there though. And the reason I had to say almost there is because if you're paying attention closely, while we've shown that you have to have one even function and one odd function, because the dipole operator itself is odd, one has to be even, one has to be odd. We've shown that. But this would also allow delta J to be any odd value, right? Not just plus or minus 1. And yet it's plus or minus 1 is the selection rule. So why is that? Well, it turns out we need another piece of information, and it's spin, right? Spin's coming up again. So it turns out that the incident light used in, for example, microwave spectroscopy to just excite a transition in the rotational state, well, each photon's angular momentum has a magnitude. Right, so photons, they have the energy due to their wavelength, right? We know about this rule, right? We know that the energy of a photon corresponds to its wavelength, right? Shorter wavelengths, that means a higher energy light. But photons also have an angular momentum due to spin. So they have a contribution to their angular momentum due to spin, and that value is either going to be h bar or minus h bar. It has to be one of these two values. So it's kind of, you can think of that the spin's going one direction or the other. Now the thing about angular momentum is, much like any other momentum, it has to be conserved, right? So if a photon gets absorbed, that momentum has to go somewhere. Therefore, that angular momentum from the spin of the photon can either make J go up or down by 1. That's it. And this is also responsible for the constraint on delta M sub J. So to put it all together, we can only observe a change in angular momentum, i.e. a change in the rotational state of the molecule, in the absence of an external field when this integral is not equal to 0. This is the selection rules, right? And for that integral to be not equal to 0, it's important that both mu hat is not equal to 0, meaning the molecule has a permanent dipole, and also that the product of those three functions, psi b times mu hat times psi A must result in an even function, right? Because the odd ones integrate to 0. And that change in momentum also needs to be accounted for by a loss or gain in the spin angular momentum of a single photon. And that single photon either has a spin angular momentum of plus or minus h bar. And so that is the equation that shows us when a transition is allowed. All right, so we've covered some of the fundamental quantum mechanics underlying rotational spectroscopy. And now let's talk about actually making these measurements. So while pure rotational spectroscopy instruments do exist, right? They're in the microwave region. They do exist, but it's actually possible to observe these rotational states using Fourier transform infrared spectroscopy. And in doing this, you have to look at the Rovibrational spectrum. So rather than saying, okay, this is vibrational or this is rotational, it's energy transitions due to both. And it turns out it's actually pretty easy to tease out the rotational contributions from the vibrational ones using this technique. And in most cases, these FTIR measurements of rovibrational transitions in gases is actually both more informative and convenient than the pure microwave ones. So that's actually what we're going to focus the rest of our conversation on. So this might sit with you funny, right? If I say, okay, this is the microwave region, that's where these rotations happen. And then I tell you that, yeah, but we can use IR to look at it. Be like, well, wait, isn't that the wrong wavelength of light to be observing these things? So maybe pause the video and think about that. Like, why am I able to do this? Why is this possible for people to make such measurements? Well, again, we're talking about the total change in energy for rovibrational. So this is both rotation and vibration. And the most important part of that line that I just displayed is that the delta E vibrational is much larger than the delta E rotational. Therefore, the contribution is going to be mostly from that. So the delta E is mostly that, and that's why we can look in the IR region. To put this into more certain terms, if we want to consider the wave number for light absorbed that'll cause the different delta E rovibrational or delta E vibrational transition, that's going to be on the order of about 1,000 inverse centimeters, right? 1,000 wave number. While the wave number separation between rotational transitions that's only on the order of like 1 to 10 wave number. Thus, if we look in that region that is in that 1,000 wave number area, and we just look for the peaks that are separated in that region, right? So for example, we might see a peak at 1,000, then 1,005, then 1,010, then 1,015, right? That's how we can see these things, is that we are actually looking in the region for the vibrational absorbance, but we're going to actually see little deviations in that are due to the rotational changes. So again, building up from theory here, this is a sort of an idealized example of what we would see in a model system where, let's say, we have a rotor, and instead of being a rigid rotor, let's say it's coupled, the two masses are coupled together with a harmonic oscillator. So we're combining two of our quantum toys right now. And if we get the rovibrational spectrum of this toy, then that's what we're going to get. We're going to get this nice, clean, symmetric spectrum. Now, there are different names here. So we have something called the R branch. If we look at the right side, well, you might say, like, wait a minute, why is this symmetric? What's going on here with these rovibrational changes? Well, the R branch are the absorbances due to rovibrational state changes where the delta E vibrational for all peaks is a single vibrational transition, right? So we're just going, typically at room temperature, you're just going from ground state up to the first excited state. So the change in the vibrational energy is actually the same for all of these. It's the rotational piece that changes. So those individual peaks represent transitions going from lower to higher energy rotational states. Remember, delta J can only be plus or minus 1. J can only change, it can only go up by 1 or down by 1. So these are the ones where J goes up by 1. And the P branch, that's the opposite now, right? These are cases where the rotational states go from a higher down to a lower rotational state. So these are the ones where delta J equals -1. So wait a minute, is this kind of weird? Let's think about this. We're looking at absorbance spectroscopy, right? So we're putting energy into a system using light, and we're seeing which wavelengths of light get absorbed, right? That's sort of what I said was basically a basic way of thinking about absorbance spectroscopy here. But now we're talking about something going to a lower state. Well, what's the deal with that? Why are we allowed to do this? Well, again, the dominant effect here is absorbance, right? We're going to a higher vibrational state. So the vibrational state in all of these is going to a higher level, right? The light is getting absorbed, putting the molecule in a higher vibrational state. That's where the light's going. But again, remember that photons have a spin angular momentum of plus or minus h bar. Therefore, when that photon meets the molecule, it can either contribute additively to its overall angular momentum, or it can take away from it. And so that's why we see both of these is, again, it's that spin of the photon being plus or minus h bar. And finally, in the middle, we call this the Q branch. So on the left, we had the P branch, and on the right, we had the R branch. In the middle, we have the Q branch. So the Q branch, this is where delta J equals 0. And take a look. Are there any peaks in there? No, there's that dotted line to kind of say like, hey, this is where it would be, right? But again, that incident photon possesses spin angular momentum. So, how can, in this particular case that we've described, like how could that be excited, right? If it's taking on that photon, it has to affect its angular momentum one way or another, right? That spin has to make its contribution. It has to go somewhere. We're back to conservation of angular momentum. So that's why we don't see anything in here. This is the Q branch. In this case, it is empty. And the purpose of this slide is just to kind of help you remember these things. So P stands for poor, meaning that this is where it loses angular momentum due to the spin, right? The spin of the photon makes it lose angular momentum. So we call that the P branch. The P stands for poor. I think it actually stands for poor in French, but it's also P and R, poor and rich. And then on the right side, it's R is rich, and these are for gains in angular momentum, right? So the rich side is gaining angular momentum from the spin. The poor side loses it. And in the middle is Q. And why is it Q? Well, Q comes between P and R, right? Element of P, Q, R, S, right? That's really it. All right, so now that we have examined the overall structure of this spectrum, namely with the P, Q, and R branches, let's look at a little more fine detail here. And let's look at the spacing and the relative intensities, right? So why are these peaks spaced apart the way they are, and why are some more intense than others? In other words, higher than others. Well, of course, the spacing is determined by the difference in energy between these rovibrational states. So, as usual, higher frequency is higher energy. And this rovibrational energy, we're just going to express that as the sum of two of our quantum toy systems, right? We have the quantum harmonic oscillator in the first term there with that nu naught times nu plus 1/2, right? That Greek letter that looks kind of like a V, it's called nu. And then the second term there is our quantum rigid rotor. In particular, that is the energy for a linear rotor, that B times J plus 1. So this combined system has two quantum numbers, nu and J. So let's look at the lowest energy transition that we can look at in the rovibrational spectrum, at least the lowest energy one, where it goes from a lower to a higher rotational state and from a lower to a higher vibrational state. And of course, I'll remind you that all of these go from a lower to higher vibrational state. It's the rotational state that can either go up or down. So let's look at the one where we're going from the ground vibrational state, so the quantum number 0, up to the first excited state for the harmonic oscillator, and that is the quantum number 1. So our final state is that nu equals 1, and our initial state is that nu equals 0. And in terms of the rotations, our initial state is that J equals 0, and our final state is that J equals 1. So if I plug these two into this equation and do final minus initial to get our delta S here, then this is what we get, right? Delta S is equal to 1/2 nu naught plus 2B. And of course, B is our rotational constant B that we've been talking about for quite a bit for our rigid rotor. So of course, this is the first peak in the R branch, right? The rich branch that gained angular momentum due to the spin on the photon. So we've explained our first individual peak there. It's that red one with the green arrow pointing to it. And now on this slide, let's look at the next transition that we can observe going higher in energy. So again, the vibrational state is just going from quantum number 0 to quantum number 1 for nu. That's the same. But the rotational state, now we're going to say, okay, what if initially we had the quantum number 1 for J, and now J goes up to 2, right? J is allowed to increment upwards by 1. So that's what we're doing here. So now if we take the difference, now we're going to get 1/2 nu naught plus 4b. And of course, we calculated the previous one, right? The one that you see up at the top there, that 1/2 nu naught plus 2b. And this new one is 1/2 nu naught plus 4b. So if you take the difference between the two of these, you get 2b, as you see in the green arrow at the very bottom. So then we could label that. We could say that the spacing here is 2b. And it turns out that's actually the spacing for all of these peaks here. So for this theoretical model where basically it is a rotor where the coupling is not rigid, but instead of being rigid, it is coupled with a harmonic oscillator, right? So it's basically a spring connecting two masses, but assuming that the spring behaves as a harmonic oscillator. And you know, another thing worth pointing out here, notice that the total energy, right, that function S, it has two separate terms. You have your vibrational term and your rotational term. Notice how they're not affecting each other, right? They're totally separate. Our model system here does not include any interaction between these two terms. So that explains the spacing. Now let's address the intensities, right? Why are some of these higher than others? Well, as you might expect, the taller the peak, the more that particular transition is occurring in the ensemble of molecules. So if we have a collection of molecules, we call that an ensemble, just like a collection of musicians is called an ensemble. So which ones are we likely to see? Well, simply put, basically you see the most transitions where the lower state is more highly populated. And of course, there's only so much energy in the system, right? So you can think of the energy being partitioned into the different systems as part of the ensemble, right? We have all of these pairs of masses attached to each other by harmonic springs. One way you can kind of think about this is that, you know, these molecules are going to have some sort of tumbling action going on. As they're a gas, right? They're free to both translate and rotate. So they've got some sort of angular momentum to begin with. And as they're translating and rotating, much like the kinetic theory of gases, right, where we say the higher the temperature of the system, the faster the average speed of the molecules, right? And they follow like a Boltzmann distribution of the speed of the molecules. Well, here it's very similar, except we're talking about tumbling instead of translating, but it still follows basically this Boltzmann type shape. So I've actually superimposed a kinetic theory of gases diagram at the bottom right there with these exact peaks shown in the model at the top left, right? So I've pasted that, I superimposed it over there, and notice how well it lines up. It's the same sort of pattern that basically there's so much energy in the system and it can be partitioned into these different rotational modes that have a kinetic energy associated with them. And then, you know, incident light comes in and it promotes it by one level. So basically it's where did it start and then can it go up by one level from there? I think the simplest way to think about this is, you know, what rotational state were they hanging out in to begin with? What rovibrational state actually, right? And then when it got excited, the vibrational went up by one level from ground to first excited, and then the rotational state also either got promoted or demoted by one, right, from where it already was. That's the best way you can think about this. Okay, so I showed you that nice, clean, perfectly symmetric spectrum, and I made a point to call that a theoretical spectrum, right, where we have basically a rotor that is coupled with a harmonic oscillator, right? Two masses attached by a spring that is also able to rotate. But now let's look at a physical system. So we have HCl, and you can see that, yeah, that's basically what we've been talking about. It has a permanent dipole, right? The chlorine atom has a partial negative and the hydrogen has a partial positive. That's permanent, right? That doesn't change. And HCl is actually a really common gas to be studied here. And why do I say HCl gas, right? Obviously, HCl you usually see in liquid form. But in the gas phase, Basically, that's what allows us to see these rotations, because if it was in the condensed liquid phase and they're bumping into each other, and yeah, sure, maybe they start to try and rotate, but then they bump into something else, right? They can't really get a clean rotation that we can observe. So you actually need it to be in the gas phase to observe this experimentally. And here's what a rotation vibration spectrum of HCl gas looks like, or sometimes called Rovibrational spectrum for short. This is what it looks like. Now, take a good look at this and remember the theoretical one. And the first thing I want you to notice is that the symmetry is now broken, right? If we look at the right, those are much more condensed than the ones on the left. That spacing between peaks is clearly tighter on the R branch, right? The R branch has, on the right, has a tighter spacing than on the P branch on the left. So that's one thing that we noticed like right away that's not quite right. The relative intensities are actually pretty good, right? The Boltzmann prediction of how much we should see of each rotational state is actually quite good. But the other thing we notice is that they're not actually just clean single peaks. It's actually pairs of peaks, right? You see that there's these pairs of peaks that are very close together instead of single peaks. So can we explain these things? So that's the whole point here. We're trying to understand what the molecule is doing based on what the spectrum is showing us. Let's start with the pairs of peaks, because that's the simplest to explain. Basically, this splitting is due to the difference in rotational inertia due to the two chlorine isotopes, right? So you can have chlorine 35, the abundance of that is about 75.5%, and then there's chlorine 37, the heavier isotope, that is 24.5% abundance. So, if you look at these peaks, these numbers actually make a lot of sense, right? So that's why we see these two things, is that these rotors are not all the same rotor. Some of the rotors have a heavier chlorine than others. As for why the spacing on the P branch is wider than the spacing on the R branch, this is going to take a deeper explanation. So we're going to address that next. So in a nutshell, there's two reasons for this discrepancy in the spacing, right? One is rotational vibrational coupling. Basically, these two things affect each other, right? That's the coupling. And the other one is centrifugal distortion. Now let's think about why the rotational and vibrational aspects are coupled here. So remember that the rotational constant for a rigid rotor in units of frequency is B tilde equals h over 8 pi squared speed of light times I. Right, and I is the moment of inertia. So I is mu times r squared. And notice, we just have that 1r squared because this is a linear rigid rotor. We're just talking about two masses here. And r is the distance from the h to the CL. So in that case, our B tilde we can write as h over 8 pi squared over c mu r squared. Thus, the larger the r gets, the smaller the B tilde becomes, at a rate of 1 over r squared. So we're talking about r changing, right? Remember back when we were doing the rigid rotor, we were like, r is a constant. We don't have to, we treated that as a constant. But remember, HCl is a rotor, but it's not rigid. And while this is quite similar to our model system, right, where we had a harmonic oscillator, right, a harmonic coupling between the two masses that was that our rotor was made up of, in this case, that 1 over r squared, that's actually going to change, and we'll get into more specifically how moving forward. And remember the spinning guy, right, from the rigid rotor video. Basically, we've seen this connection before between rotational inertia and the distance between the masses before. So this coupling, we see it right here, that he can do some work, right? He can apply a force over a distance, pulling those weights in, and then his conservation of angular momentum makes him rotate faster. But there's an important thing here with this coupling that I want to address on this particular slide, and that is that our rotor, our model example, we had a harmonic rotor, right? A harmonic potential energy function looks like the function at that top right? It's perfectly symmetric. Right? Remember that was the one where if we took the expectation value of x, it was exactly the equilibrium distance of x, no matter how high the vibrational state was. Right? We always expected that mean, that our expectation value of x to be in the same place at the equilibrium length. But this is actually not true for covalent bonds here, because covalent bonds do not behave like harmonic bonds. If you look at very small vibrations where they hang out in the lower energy states, right? So if you look at that diagram at the very bottom with that green harmonic oscillator where it's bouncing back and forth, if you look all the way at the bottom there and you compared that to a harmonic plot, right? Like that red plot at the top right, if you compared those, it would look very similar, right? It'd be a little bit distorted. You'd see that the right side's actually a little more stretched. It's not quite symmetric, but it's pretty close, right? But if you go to the higher vibrational states, right? If you get towards the top of that, that's very, the asymmetry really comes out up there. So this is known as anharmonicity, right? Not harmonic. And these sort of behaviors really affect the way bonds vibrate. And that expectation value of your bond length, that actually will go up for higher energy states. So as we said with the model system, the harmonic oscillator, nope, same thing. No matter how high the energetic state goes, the expectation value for the bond length is the same. But this is not actually how it goes with a physical system. In particular, this very simple physical system of HCl gas. Right? The higher vibrational states, the expectation value for bond length actually goes up. Therefore, even if we think of that R value as being like the average bond length, right? That's changing now. So the larger R gets, the smaller B tilde becomes, right? The smaller the rotational constant becomes at a rate of 1 over R squared. And so this is what we see here. So that potential energy function called a Morse potential, this is also not exactly the shape of a molecular bond's potential energy function, but you can fit them quite close. You can get a good approximation with a Morse potential. So you might say, hey, if we have a Morse potential, well, why were we using a harmonic approximation all this time? Well, the harmonic one is much simpler to work with mathematically, and it's also simpler to work with computationally. If you're going to write a software program that simulates how molecules vibrate, if you know that your molecules are going to be hanging out in those lower energy levels where the difference between a Morse potential shape and a harmonic shape are very close, you can save a lot of computational power by just modeling it using harmonic bonds. In fact, one of the Nobel Prizes, I think it was 2013, went to the field of molecular dynamics, where this sort of approach has been done for years on biologically relevant models like proteins and things like that. All right, so now we're on to centrifugal distortion. Well, this one's actually pretty quick to explain. That basically, let me show you a video instead of talking about it. So if you look at this remote controlled car here, he's got some really powerful electric motor, and the faster he spins it, the faster the tires spin, and look, they're actually deforming. So if you were going to measure like the radius of that tire, it's actually increasing with its angular momentum, right? So this is centrifugal distortion that basically that connection between the two masses is getting longer the faster it spins. So, we have the rigid rotor is long gone now, right? We're talking about rotors that can stretch, and this is what centrifugal distortion is. All right, so now we have some intuition for why the experimental rovibrational spectra of a linear rotor molecule like HCl is not behaving like the theoretical model, or at least it's very similar to it, right? The theoretical model is still very useful because we could say, okay, if it was this perfect harmonic bonded rotor, it would behave like that, and then we can look at the experimental one and say like, okay, it's close to that, but why is it different? This is a very useful tool for understanding things, but it's really important to try and understand why it's different. So let's do a little bit of math here and show the energy differences and compare what's happening in the P branch versus the R branch. So again, here's our energy function that's just the sum of the harmonic energy levels plus the rigid rotor energy levels. Now, if we consider the R branch, this is where delta J is +1, right? It's going to a higher angular momentum energy. And then we do, final minus initial, our usual final minus initial, and we see what that works out to. So if we plug all of the right quantum numbers in here, we see that this is the difference that we'll be taking. And I encourage you to pause the video, at least work through the math in your head to show prove to yourself that you understand what each step is doing, and maybe even write it out yourself is probably even ideal. But just to give you an overall sense here, you see how we've got your final is where J went up by 1, the first J, right? That's this J, went up by 1. And then the J plus 1 also went up by 1, right? So it's shown as plus 2. So it's like J plus 1 is how you can kind of think of it. So we added a 1 to this J, and we added a 1 to this J that already had a 1 added to it. That's why we have that. Then we take the difference, we subtract the one where we did not add 1 to the J, and we get this. Also, you'll notice that this 3/2 nu tilde came from having a 1 for this nu, and this one had a 0 for that nu. Then if we simplify this a little bit, we get this expression here. So let's interpret it now. This is the shift in frequency. So we have our base frequency, that nu tilde, and then the rest of these terms are the shift. And note that the final J squared term is going to be the one that dominates, right? J is an integer here. And so J squared is going to be larger, right? We know that J isn't going to be a decimal, right? Because if you square a decimal, it gets smaller. But that's not going to happen here, right? This is quantized to integer values. Also, note that first term, that 2b tilde, right? That's just our usual shift, right? Remember our theoretical model showed us that it was going to shift by 2b, right? We showed that the gap between each of the peaks was 2b. So that nu plus 2b, this is just our theoretical prediction. But then if we look at these other corrections here with these j's, all right, now we're seeing like what's going on with the experiment here that is making it deviate from the theoretical prediction. And so that J squared term, that is going to be the one that dominates. And it also turns out that B naught is smaller than B1. And why do we know this? Well, as we showed in a variety of different ways, the higher vibrational states have a larger R. So the higher vibrational states have a larger R, and the larger R for the quantum state nu equals 1 is going to make B1 smaller than B0. All right, so pause the video, maybe really think about that. Make sure you understand this. This might take a moment. Definitely really think about it. Stare at these equations till that makes sense to you. And again, I've included the equation for the rotational constant B at the end there so that you can look at that and see like, oh yeah, okay, that makes sense. And again, right, the rotational constant depends inversely to R squared. So if R squared gets bigger, B tilde gets smaller. And because we know that it got excited from nu equals 0 to nu equals 1, then we know that B1 must be smaller than B0. So what this tells us is that this correction, all these terms that we've shown in the correction, that again, J squared term is dominating, that's going to be minus some constant times J squared. So that means that our correction to nu plus 2b, right? Nu plus 2b was the theoretical prediction. The rest of it's a correction. That correction is going to result in making that gap a little smaller. And this is what's going on in the R branch. And yes, this is what we see, right? If you compare the R branch with the P branch, clearly the R branch, they're bunching together, right? That gap is getting smaller. And that's the term that explains why, right? B1 minus B0 is going to be negative, and J squared is going to get larger and larger, right? Because J can't be a decimal. Therefore, the gap gets smaller and smaller for higher and higher energy rotational states for the R branch. And that explains why it is closer together than compared to the theoretical model, and also closer together compared to the P branch. So now if we look at the P branch, you know, we do the math in a similar way. And again, I encourage you, take the time to write all these out, make sure that you get the same expression, right? Work through this yourself. But looking at it, we get kind of a similar thing, but in the opposite direction. Again, we get this J squared term. And again, B1 is smaller than B naught. Therefore, that term's going to be negative. You might say, wait, this sounds just like the other one, but it's different. Well, it is different, right? Because note that the final J squared term still dominates. So that's the same. But if we're talking about going to the left now we're talking about decreasing in J, right? Because remember, when that photon gets absorbed, the angular momentum due to the spin of the photon can either increase or decrease the rotational angular momentum of the molecule that's absorbing it, right? So this is the case where it's decreasing. So we're decreasing in J, which means that the amount that we subtract, this correction gets smaller and smaller with decreasing J. So this is why in the P branch, that gap gets bigger, right? That shift between peaks gets larger with decreasing J. And again, it's that same justification. So again, I suggest you pause the video, really stare at these equations and make sure that they make sense to you. And so that's why we see this asymmetry in the spectrum that we do not see in the theoretical predictions. So at this point, although there is so much more we can do with rotational spectroscopy, I thought this is a great place to end it because we've fully explained the Rovibrational spectrum of HCl here. So thank you so much for watching. I hope you enjoyed the video. I'm Dr. G, and I'll see you in the next one.